Welcome to tutorial 9, the last tutorial in this course. In this one we discuss about diagonalization of matrices. Let A be an 3 by 3 real matrix such that A times ABC transpose is equal to A plus B plus C, A plus B minus C and A minus B plus C for all A, B, C in R. Diagonalize A if possible. So, here your first task is to find out whether it is diagonalizable. If yes, find a matrix P such that P inverse AP is a diagonal matrix. So, first understand what is A. A is given by, you can write its columns as AE1, AE2 and AE3. So, apply AE1, what you get is 1 1 1, AE2 is 1 1 minus 1 and AE3 is 1 minus 1 1. So, the matrix A is here and then compute its characteristic polynomial, and you can see that the eigenvalues are minus 1 2 2. Now, as we have done in the last lecture and the earlier tutorial, you can compute the eigenvectors by solving Ax equal to minus x and Ax equal to 2x. So, the first eigenvalue, take eigenvalue lambda equal to minus 1 and solve the system Ax equal to minus x. Then you get eigenvector minus 1 1 1. We are not going through the entire process of solving, but then when you are doing it, you should go through that process completely. Do not simply believe that this is the eigenvector, you should verify it. And for lambda equal to 2, one can obtain two linearly independent eigenvectors. Again, here these are not the unique ones, you may end up getting a different pair of eigenvectors. But in any case, it will be a system where you can get two linearly, a system of there will be one equation with three unknowns, and then using that we can get two linearly independent vectors. So, we can take the matrix P as minus 1 1 1, 1 1 0 and 1 0 1 as the columns of the columns as these vectors, and then we have already proved that by theory we have shown that if I take these as eigenvectors and if these are linearly independent, then they are, the matrix is invertible and P inverse AP will be a diagonal matrix with the diagonal entries as eigenvalues in the appropriate order. So, here we have taken the first column as eigenvalue corresponding to eigenvector corresponding to eigenvalue lambda equal to minus 1, and then eigenvectors corresponding to eigenvalue 2 and 2. Therefore, P inverse AP will be diagonal matrix with diagonal entries minus 1 2 2. If you you should verify this, that P inverse AP is indeed this. You can also verify that if you take the matrix P as the first column as 1 1 0, second column as minus 1 1 1 and third column as 1 0 1, then the diagonal matrix that you get by taking P inverse AP will be diagonal 2 minus 1 2. This you should verify it. You should take that matrix, find the inverse, and then you can verify that P inverse AP will be diagonal 2 minus 1 2. Okay. So this matrix is diagonalizable, and we have obtained matrix P such that P inverse AP is diagonal. Now let us look at the next problem. A is a real 3 by 3 matrix such that A times E1 is 0, A times E2 is E1, and A times E3 is E2. Diagonalize A if possible. Now what is A? The first column of A is the 0 vector, second column of A is E1, and third column of A is E2. Therefore, A is the matrix 0 0 0, 1 0 0 and 0 1 0 as columns. Now, this is a triangular matrix. So, therefore, the eigenvalues are precisely the entries on the diagonal. Therefore, 0 is the only eigenvalue, and it has algebraic multiplicity 3. The characteristic polynomial is nothing but x cube, right. So, therefore, this is the 0 is the only eigenvalue. Now, we make a simple observation. Suppose this is diagonalizable, then what would that mean? There exists a matrix P such that P inverse AP is diagonal matrix with diagonal entries as the eigenvalues, but here the eigenvalues are all 0. Therefore, P inverse AP will be 0 matrix. But when P inverse AP is 0, what does that mean? A must be 0, right. A is similar to a 0 matrix, but then the only matrix similar to the 0 matrix is the 0 matrix, because P inverse AP is 0 implies that A must be 0, because you can obtain that by pre-multiplying and post-multiplying by P and P inverse. We get that A is 0. Therefore, the conclusion is that A is not diagonalizable. Now, let us look at the next problem. I take this matrix A with the property that A E1 is E3, A E2 is E2 and A E3 is E1. Diagonalize A if possible. Again, from the given conditions, we can immediately write down the matrix A as 0 0 1, 0 1 0 and 1 0 0. These are the columns. Now, compute the eigenvalues. You can immediately, it is very easy to compute the characteristic polynomial, and you can see that the eigenvalues are minus 1 1 1. Now, take the eigenvectors for each eigenvalue, solve the system Ax equal to lambda x, and then find eigenvectors. You can see that minus 1 0 minus 1 is an eigenvector corresponding to the eigenvalue minus 1, and 1 0 1 0 1 0 1 0 are eigenvectors corresponding to eigenvalue 1. So, therefore, if you take the matrix P, so we have got 3 linearly independent eigenvectors. Therefore, if I take the matrix P as these as columns 1 0 minus 1 1 0 1 and 0 1 0, then P inverse AP is diagonal matrix with diagonal entries minus 1 1 1. One more observation that we can make here is that A is a symmetric matrix, therefore A is diagonalizable. That's already known to us. In the last lecture we have seen that we have not proved, but we have stated that it is Hermitian matrices are diagonalizable. And in fact we stated something more, that we can choose the matrix P in such a way that it is orthonormal. Now in this case the matrix P is not orthonormal, but you can actually see that the vectors that we have taken, they are orthogonal. Now if you want to get a matrix which is orthonormal, or P as orthogonal matrix, you want to normalize these vectors. So if you take P as 1 by root 2 0 minus 1 by root 2, 1 by root 2 0, 1 by root 2 and 0 1 0, then P will be an orthogonal matrix. P transpose P will be identity, and P inverse AP or P transpose AP will be again diagonal matrix with minus 1 1 1 as diagonal entries. Now let us look at the next problem. Diagonalize the given matrix if possible. So this one we are not giving you the entire solution, we will only give you the eigenvalues and then compute eigenvectors and compute P. That will be left as your job. First we can make an observation that it is diagonalizable because it is a real symmetric matrix. Now it is our job to compute the eigenvalues, corresponding eigenvectors, and then compute P inverse AP. So in this case the eigenvalues are lambda equal to 2, minus 1 and 2. For each lambda, solve the system Ax equal to lambda x and compute the eigenvectors. So here again this is a real symmetric matrix. Try to get an orthogonal matrix P such that P inverse AP is diagonal. Let us look at the next problem. Is 1 1 0 0 1 1 1 0 1 diagonalizable? Let us first compute the eigenvalues. Eigenvalues of this matrix are 2 1 plus root 3 I divided by 2 1 minus root 3 I divided by 2. These are the eigenvalues. Now we have three distinct eigenvalues. This is a 3 by 3 matrix and it has three distinct eigenvalues. So here this example says that you will have to look for eigenvalues in the complex numbers, complex space as well, and similarly the eigenvectors. Okay, so we have, this has three distinct eigenvalues, therefore it is diagonalizable. To begin with, we can say that it is diagonalizable. Now the eigenvectors have complex entries, so the diagonalizing matrix P will also have complex entries. Now for each eigenvalue lambda, solve Ax equal to lambda x and compute P. Okay, we leave that job to you. This example particularly is to tell you that even if a real matrix is diagonalizable, the diagonalizing matrix need not necessarily be a real matrix. So, this is an example to show that the eigenvalues can be complex, eigenvectors can be complex, and the diagonalizing matrix can also be complex even if the matrix is a real matrix. Let us look at another problem. Give an example of an n by n matrix that cannot be diagonalized. So, how do you construct a matrix that cannot be diagonalized? Okay. So, let us look at one of these tutorial problems that we discussed a little bit earlier. We looked at this matrix A with the property that A times E1 is 0, A times E2 is E1, and A times E3 is E2. That means you constructed an upper triangular matrix with diagonal entries as upper triangular matrix with diagonal entries as 0. Therefore, the matrix is if the matrix is diagonalizable, the diagonal matrix must be the 0 matrix, but there cannot be a non-zero matrix which is similar to 0 matrix. We can take the same strategy now. In an n by n matrix, you can either generalize that to construct an upper triangular matrix with 0 as diagonal entries, and then say that it cannot have it cannot be similar to the 0 matrix. Using the same idea, we have another matrix. We have n by n matrix whose diagonal entries are 1, but there is one more non-diagonal entry with 1. You can take it to be anything. But now, if you look at the eigenvalues, they are nothing but 1 with algebraic multiplicity n. Which means that if A is diagonalizable, P inverse AP must be equal to identity, right? But then can we have P inverse AP equal to identity and A is not equal to identity? If P inverse AP is identity, again pre-multiplying by P and post multiplying by P inverse, we can see that A is equal to identity matrix, but A is not an identity matrix. Therefore, A cannot be diagonalized. So, this concludes the final tutorial. Do more problems from the reference and textbooks, that is given, the list is given at the end of the class notes, and then get back to your teacher if you have any doubts. They should be responding to you within a reasonable time. Wish you all the best.